got his PhD in Princeton, and right now postdocs in MIT, joined faculty at Perimeter, before moving to this position he's had. And just the most creative cosmologist in these famous ones, things like the music mechanism.
We don't know many cosmologists.
For making fit forces interesting in cosmology, that is, being able to highlight local tests which are very strange. And today, Jesse's going to talk about new approaches to dark matter.
Well, thanks a lot, Dwayne. Thank you very much for the invitation. It's always a great pleasure to be back in Chicago. So the work I'll present is work I've been doing for the last 2 years, in particular with our former postdoc, Lasha Verjian. And I'll also discuss some ongoing work with all these people. So I'm from the University of Pennsylvania. If you've never been to UPenn, our physics department is housed in the David Rittenhouse Laboratories. And if you're looking for it, it's basically a building that more or less looks like this building. Come on, this is not their building again. But the risk of spelling it out. Okay, in fact, I'm taking many pictures during the script to bring it back to the deans. So by now, there's clear-cut evidence for the existence of dark matter. I think it's fair to say that the greatest phenomenological success of dark matter actually comes from the largest scales. So from the beautiful microwave temperature anisotropy peaks to the matter power spectrum. But if you think about it, on those scales, really, on those linear scales, we're not really using the particle nature of dark matter. In fact, if you open any textbook on cosmology, we can well describe dark matter simply in some hydrodynamical limit as a perfect fluid with some energy density and some pressure. And so in fact, any perfect fluid with sufficiently small pressure and sound speed would do equally well at fitting these large scales observables. The corpuscular or particular nature of dark matter really comes in when we do simulations, starting from millions of particles in nearly homogeneous initial conditions. Let those evolve under gravity, you have Jeans instability, which eventually leads to the formation of this beautiful cosmic web with filaments and halos, which later form, which are the homes for galaxies in the late universe. So we can ask, how does this particle nature of dark matter do against observations? So one thing that is striking about galaxies in our universe is that they're remarkably diverse, but at the same time, they're strikingly regular. And this is embodied in various scaling relations, scaling empirical relations that are observed, the most famous of which is probably the baryonic Tully-Fisher relation, which tells us that the asymptotic velocity, rotational velocity in galaxies to the fourth power is related to the total baryonic mass in those galaxies. That includes stars and gas. This relationship empirically has been shown to hold over 6 decades in mass with remarkably small scatter. Okay? Now, the dashed line in this plot represents the naive prediction from CDM, from cold dark matter, in which you take as a mass of the baryon the cosmic baryon fraction, so roughly 1/6. And so you see that the mismatch of the dashed line to the actual observable is really a proxy for the statement that there are missing baryons. Baryonic feedback processes have pushed out baryons in a way that is more pronounced at low mass. Okay? It has to do so in a correlated way in order to reproduce this particular v to the fourth scaling. Okay? The prediction would be v to the d cubed, so there has to be preferential feedback for low mass galaxies. In more detail, if you go beyond just Tully-Fisher, one of course has to look at detailed rotation curves. And it's well known that rotation curves of galaxy are asymptotically flat, corresponding to an isothermal profile, while pure CDM simulations, just n-body simulations, result in this famous universal NFW profile, which goes as 1 over r in the inner regions of the galaxy and asymptote to 1 over r cubed in the outskirts. So what is clear from these pictures is that both the Tully-Fisher relation and the detailed rotation curves, baryonic processes, supernovae and feedback, have to play an important role in galaxies, in actual galaxies. Over the last few years, there's been tremendous progress in doing hydrodynamical simulations, including a host of complex baryonic processes, and eventually the end result of this may be that we find that through all these processes, this complex physics, emerges galaxies like the ones we observe with those particular scaling relations. This may well be the outcome. It could be, for instance, that the Tully-Fisher relation, the scaling relation, emerges in some way from this complex processes, the same way that Kolmogorov's law emerges from turbulence. Okay? But it's one thing that is, to say, puzzling at this stage is that these feedback processes are inherently stochastic. They should vary, they should depend on their environment in some way. So how do they conspire, despite their stochastic nature, to give rise to tight scaling relations in the way we observe? So in other words, it may well be that you would find p to the fourth as the mean relationship, but you would expect some pretty significant scatter given the stochastic nature of these processes. At least that's the naive expectation. And indeed, this is the suite of simulations done last year, like the Illustris collaboration. The dots are the simulated galaxies. These are all pretty massive galaxies. This is to be compared to the yellow band, which is the McGaugh sample, and you can see the scatter indeed is significantly larger than what is observed. Again, beyond the Tully-Fisher relation, you can look at individual galaxies. This is from a paper of just a few months ago. This is a collaboration that includes Navarro, Frank, and White. And you can look at the detailed rotation curves for dwarf galaxies, and this plot nicely illustrates the diversity of dwarfs. So here you have 4 galaxies, 4 dwarfs, whose asymptotic velocity is nearly the same in all cases. So these, in the CDM picture, means that these form in halos that are similar. Okay, so one would expect that these galaxies form in roughly the same dark matter halos, and yet at the end of the day, the distribution of baryons, they all have the same baryonic mass. The distribution of baryons is completely different. Here you have a steeply rising rotation curve. Here it's a very flat, linear growth, essentially. The shaded regions are what the simulations, the output of the simulations. The band here represents how much feedback. This is like a range depending on how much feedback there is. One thing that's to notice is that you see that the feedback does change the normalization of the rotation curve, but it doesn't change the shape very much. So this is again some sort of similar property of rotation curves. Whereas the actual rotation curves can be quite different from high surface brightness galaxies to these low surface brightness. Okay. Of course, there are also, for many years, for decades really, there have been these so-called small-scale controversies. I'm not going to spend much time on them. The idea of matching the number and population and the distribution in mass and so forth of the satellites around large galaxies like the Milky Way. One thing that is interesting is the actual spatial distribution of these dwarfs. It's been noticed, actually going back to the 70s, this problem has sort of become sharper, that the dwarfs around the Milky Way galaxy, so in the local group around the Milky Way and around Andromeda, are not isotropically distributed, as you would naively expect from simulations, but rather they lie along thin planar structures, vast planar structures like so. In fact, the plane of Andromeda points towards the Milky Way, which is funny. Furthermore, the dwarfs within Andromeda, the majority of the dwarfs shown here, you see they have the red ones, they have a common angular momentum. They're co-rotating within these planes. Now, maybe this is all just a coincidence, a chance alignment. In fact, to be fair, we don't expect dwarfs to be completely isotropically distributed. There are, after all, sources of anisotropy in the large-scale structure, in particular filaments. But the problem, in some sense, is one of scale. The filaments are huge in size compared to the size of the plane. So it's a little bit like saying that in Rome, one particular avenue in Rome points from northwest to southeast, and that's because Italy points northwest, southeast. Okay, so it's that kind of mismatch of scales. Anyways, these are just, at the end of the day, again, these are curiosities, things to keep an eye on. There's a completely different proposal, a radical proposal, which is known as MOND, Modified Newtonian Dynamics, or the way I prefer to think about it, as an empirical law. And it's a statement proposed back in the 80s that, so this is very radical, the proposal was that in fact there is no dark matter in this picture, but instead that the behavior in galaxies is governed by a modification to Newtonian dynamics. The modification is that at high acceleration, you approach Newtonian acceleration, but below, much below some critical acceleration A0, you revert to a geometric mean of the characteristic acceleration and the Newtonian acceleration. Now, just to see first why, in some sense, this does reproduce the coarse properties of galaxies. First of all, if you take a particle which is orbiting a galaxy deep in the Mond regime, where we equate the centripetal acceleration to the geometric mean expression, then clearly the powers of r cancel, and one predicts a asymptotically flat rotation curve. Okay? Furthermore, if you square this relationship, it tells you that the asymptotic velocity to the fourth power indeed scales like the baryonic mass, so it has as a prediction the baryonic Tully-Fisher relation. In detail, if you now look at fits of rotation curves, I think one of the successes of Mond is that indeed it manages to fit with just a single parameter and the mass-to-light ratio for each galaxy. It manages to fit equally well so these high surface brightness galaxies as well. This is exactly the galaxy I was showing you earlier with the rising profile, and it does equally well at fitting a broad class of these galaxies. And from a theory point of view, the one tantalizing aspect is that this characteristic acceleration turns out to be of the order of the Hubble parameter today. Okay? This is just an empirical fact. Now, I think personally, if this had been presented as an empirical law as opposed to an alternative to dark matter, it wouldn't create such big controversy and fights and so forth. Okay? It's just, to me, a fact about galaxies. And again, at the end of the day, all these baryonic processes, if it's just CDM and no extra physics, they conspire to give this empirical law. Okay? This has to be eventually explained. Now, let me just say how you would get such an effective force law in a theory of modified gravity, so to speak. So this is the simplest theory that gives rise to Mond. You consider, let's say, a scalar field, which will be mediating an extra force beyond gravity. That scalar field must have a very funny effective theory. It has a non-analytic power of the kinetic term. Okay, so from a field theory point of view, already your hair should rise, right? And it's coupled, so this scalar field couples to density in this particular way. So to see that this gives rise to Mond, let us just vary the action to find an equation motion for a static spherically symmetric configuration. You find, of course, a nonlinear Poisson equation of this form, and because, if you want, the argument is grad phi squared, when you integrate to get Gauss's law, you find that the grad phi is in fact proportional to the square root, which is what you want in the square root of the Newtonian acceleration. So if you take this acceleration mediated by phi, and you add it to the Newtonian acceleration, you get a total acceleration that looks like this, which indeed satisfies the limits. When the acceleration is large, you get Newtonian, and the other regime, you get the square root. Okay? So this is the simplest way. Now, as I said, this is very controversial, okay? And so sometimes when I work on this, I feel a little bit like, you know, you have kids in the schoolyard, they say, you know, look at who Khoury is hanging out with these days. So just for the record, okay, I disavow, okay? I disavow. So, just to be clear, indeed, let's play devil's advocate. It's not all roses with Mond, and it's well known there are many problematic systems, so let me be clear about this, because ultimately I'm not going to propose just Mond. Okay? It will be something much, you know, will have important differences. The first problem is with galaxy clusters. Galaxy clusters, for the most part, are in the Mond regime, so you should be able to predict, in particular, the temperature profile in clusters. And instead of reproducing the isothermal profile, which holds over large distances within a cluster, the Mond law predicts a rising temperature profile. So that is problematic. The relativistic extensions are particularly repulsive, okay? It's not something that you'd ever come up with as a field theory. And to be fair, this was more perhaps of a proof of principle that you could get a relativistic extension of the model. But it's not something that you would write down out of the box, okay? There are other astrophysical objects that pose problem for Mond. Most famously, perhaps globular clusters. Globular clusters, some of them are as massive, they have 1 million stars, they're as massive as some of the dwarfs, but as far as we can tell, they're well fitted by Newtonian physics. Just with baryons, there's no need for dark matter. Okay, so from one point of view, you know, the fact that Mond does well with dwarfs, but doesn't do well with globular clusters, it's a puzzle. The Tully-Fisher relation, which holds very well over all these decades of mass, at some point, there appears to be signs of breakdown at very low mass for dwarf spheroidals around the Milky Way, as well as the ultra-faint dwarfs that have been discovered in the last few years. Now, to be fair, these ultra-faint dwarfs, these are tiny galaxies. You see, they have about 1,000 stars, okay? Some of them may be undergoing tidal disruption. Are they really in equilibrium? Am I justified in applying this small story to these objects. It's not clear, but suffice to say that there is tension going on at the low mass end. Okay? Tidal dwarf galaxies, when you have through tidal stripping, you can strip material away from the host galaxies. You strip the baryons, but not the dark matter. And in the stripped material, you can form recycled galaxies. These are known as tidal dwarf galaxies. These are these guys over here. They're expected to have very little dark matter in the standard picture. Yet they should be dwarfs in the Mon sense. They should have the Mon behavior. And they don't, as far as we can tell. So again, these are sort of problematic systems. Okay. Now, of course, the next natural step is to say, well, what about some hybrid model? Why not have both Mon and dark matter? Why not? Well, many people have thought about this, myself included, and of course this raises another can of worms. Of course, you should ask immediately about Occam's razor. Now you need two ingredients. Before, maybe just known physics could do the trick. Now I have to have two ingredients. Do they have a common origin? After all, it looks kind of ad hoc to have two unrelated ingredients put together. And there's also a phenomenological problem to this approach, which is that the Mon and the dark matter have to be active in different regimes, you see. We've already said that on large scales, it should be mostly dark matter with little room for Mon. Similarly, on cluster scales, it should be normal dark matter yet again. By the time you get the galaxy, it should be mostly Mon. And finally, when you get to the solar system, in the solar system, the Monnian correction, of course, is small, because the solar system is mostly Newtonian. But even that small correction is too large to fit planetary orbits. Okay? So there has to be some kind of exclusion principle, that one works, the other shuts off. Okay? So how do you achieve that? Okay, so what I want to present today is a unified approach to the Mon phenomenon and dark matter through superfluidity. So you could say I'm a unifier, okay, not a divider. So we'll see that in fact, so indeed, right, so where do people diverge? Where does the fight start? The fight starts when people say, Mon is fundamental. Other people say, no, it's emergent from all the baryonic stuff. Okay, that's where the fight. Nobody really disagrees that Mon works. I'm in between. I want to say that it's fundamental property of dark matter, but it does emerge from dark matter. So it's kind of middle ground. Superfluidity is probably the most striking manifestation of quantum mechanics. You cool down liquid helium below critical temperature, and at some point the liquid behaves completely differently. It comes to a stop, comes to a halt, and at that point you should no longer think of the liquid as made up of individual atoms. It really behaves collectively. Its excitations are collective excitations. It's really described now by a common wave function. Okay? There are two conditions for dark matter to form a condensate, to form a Bose-Einstein condensate. Why is it not so crazy to think about dark matter being a Bose-Einstein condensate? Well, the first condition is that the dark matter should be sufficiently light such that it's the Broglie wavelength set by the virial velocity of dark matter particles in a halo. The Broglie wavelength should overlap. So if you plug in, indeed, the virial velocity of a particle in a galaxy, you demand that the Broglie wavelength be larger than the interparticle separation of dark matter particles, you get an upper bound on the mass. So at the end of the day, these particles must be axion-like particles. They have a mass of order electron volt. Okay, they're not WIMPs. They have to be sufficiently light. They're not the QCD axion, by the way, but they're axion-like particles. So indeed, at a given mass, pick a mass for the dark matter particle, you can show, indeed, that sufficiently light halos, therefore virial velocity will be small enough, those will be condensing, but large enough halos where the virial velocity is large will not condense. Okay, so there's a distinction now between low enough mass halos and very massive halos. The second condition to achieve a Bose-Einstein condensate is that you should have thermal equilibrium, or at the very least that the rate of transition to the lowest, to the ground state should be sufficiently large to populate that ground state. So this, of course, puts a bound on the interaction rate of the stuff. It has to be larger than the dynamical time for a particle to go around the galaxy, because we want, of course, this fluid will be perturbed by all the baryons in the galaxy. It has to remain coherent over galactic scales. So that's the condition. It translates into a bound on the cross-section per unit mass, which, interestingly enough, is around the bound that people talk about for self-interacting dark matter. It's in that ballpark. Okay? You find, as it's very easy to show, then, that the critical temperature to form a Bose-Einstein condensate, in this case for dark matter, happens to be millikelvin. which is intriguing because known cold atom systems in the laboratory have similar critical temperatures. In fact, I'm going to argue that cold atoms may offer more than just a simple analogy. In some ways, my dark matter will behave exactly like a cold atom system. Okay, so now, again, as we've said, you shouldn't think of individual particles anymore. If you're in a superfluid, you should think of collective excitations. And this is a spectrum for liquid helium. At low energy, you have phonons. These are the dominant excitations. And you also have massive quasi-particle excitations known as protons. One thing that is known from this, and this is encapsulated in the two-fluid model of Landau, namely, you should think of, even though this is just one stuff, there's no way you can separate, it's all liquid helium, or just dark matter. Phenomenologically, if you want to ascribe it the classical description, it behaves as two fluids at finite temperature. There's the condensate fluid, the Bose-Einstein condensate, and then there's the normal fluid, which consists of the excitations on top of it. The fraction of particles in the condensate relative to the total number of particles is a function of temperature. This is for a free Bose gas. It's a famous expression, textbook expression, that is 3/2 power. So indeed, again, if you look at the function of the mass of the halo, so if you want, as you go to higher mass, the temperature of the dark matter is higher. As you go to higher mass, the fraction of particles in the condensate goes from 1, it's all condensed, and then it drops sharply as you go to higher mass. Okay? So indeed, if you pick a mass of order electron volts, or a fraction of electron volts somewhere here, you see that galaxies are mostly condensed, they lie at this end, but galaxy clusters are in the normal phase. That's a distinguishing thing about galaxy clusters with galaxies in this theory.
Are they actually penetrating each other, or how are they mixed?
What mixes? They're totally mixed. I mean, you ascribe it to classical reality, yeah, you see these normal particles are moving around in this other fluid, exactly. The equations of motion are hydrodynamical equations of two-coupled fluids. They interact and so forth. This is just for a free Bose gas, by the way. We're doing the calculation to include interactions. It's actually very interesting. And this is with a former student here, Vinicius Miranda, who's full of energy. Okay, so let's describe a little bit the effective description of superfluids. This has been known for a long time. So it's very interesting. So how to describe in a field theory language the low energy description of a superfluid. So first of all, I have to describe a superfluid from a field theory point of view. From a field theory point of view, a superfluid is described by a system that has a global U1 symmetry, and that U1 symmetry is spontaneously broken. So you know that the low energy degree of freedom will be a Goldstone boson for that U1 symmetry. I'm focusing on abelian superfluids, by the way. So there will be a Goldstone boson, which of course enjoys a shift symmetry inherited from the U1 symmetry. Okay? So there's a Goldstone boson. But moreover, to be superfluid, the superfluid state has a finite charge density under that U1. Okay, so the charge density, you can easily show, of course, will be proportional to the time derivative of the Goldstone. So what we're basically saying is you work on a background where the Goldstone has finite time derivative. By field redefinition, you can make that background just linear in time, where the coefficient nu is identified as the chemical potential, and the departures, the fluctuations away from this background will be the phonons. So at the end of the day, it's a theory of phonons at finite chemical potential described by this theta field. Now, by the rules of effective field theory, at low energy, I should write down all possible operators that are consistent with this symmetry. Okay, and so of course at low enough energies, so by the way, to respect the shift symmetry, theta must always come hit by a derivative. And at low enough energy, I should only consider terms that have one derivative per theta. Terms that have more derivatives will be suppressed in the derivative expansion. So this is the most general effective theory for a superfluid. It's a P of X theory, where X is this. Here I'm taking the non-relativistic. I'm only going to focus on non-relativistic superfluid. So it has this Galilean invariant kinetic term, and it has the mu term coming from the chemical potential. The type of superfluid is encoded in the choice of P of X, if you want. The equation of state is encoded in the choice of P of X. Okay. This is a zero temperature, I should say, zero temperature effective action. Okay, so the conjecture, and it's a conjecture, I'll be completely honest, is that the superfluid phonons of dark matter are governed by the Mond action. Okay? This is precisely the idea that, remember earlier on I showed you that the Mond action was d phi squared to the 3/2. Well, I want to say this is exactly a P of X, and so I want to conjecture that the superfluid phonons of dark matter are governed by this effective action, okay? And the phonons couple to baryons in this way, in a way that breaks the shift symmetry. It breaks it explicitly, but it's suppressed by M-plot. So it's a very weak breaking. Okay? It's a very soft breaking. And the scale lambda, so really, to keep track of scales here, there's a scale lambda, the mass of the dark matter particle, which we said was electron volts, and lambda must be chosen to be of order milli-electron volt in order to get the critical acceleration to be A naught, the one that is favored by observations. Okay? Now, this theory, so where am I getting at, right? So I told you earlier on this was a pretty ugly theory when we thought about it as a theory of a scalar field. But as a theory of a superfluid, it's not so crazy. In fact, it's completely digestible in the following sense. So first of all, it has some nice symmetry properties associated with it. If you take the limit of gradients dominating, this theory has a Weyl invariance associated with it, so you can rescale spatial coordinates by an arbitrary Weyl factor. The theory is invariant. The global part of that Weyl invariance, of course, is SO4-1, which is intriguing for the experts because that's the group of the Sitter space. So it may connect to dark energy in some way. But from a superfluid point of view, what's interesting to me and really what caught my attention is that there are actual systems in nature that have fractional powers of kinetic term, extra fractional power. The most famous example, in fact, was studied by Gamson, is x to the 5/2. It's the unitary Fermi gas. We take a gas of fermionic atoms, you tune it to infinite scattering length, and at that point the system enjoys a scaling variance, and so the effective theory for the superfluid is fixed by symmetry to be x to the 5/2. So here, if you want it, it's x to the 3/2. So it's tantalizing that known cold atom systems have fractional powers in the same way that this Mon system seems to indicate. Okay, so once you know the equation of state of the superfluid, once you specify the P of x, you know its pressure as a function of chemical potential, you know the number density, you know all the thermodynamic quantities. So you can, so in particular the equation of state, you can derive it. It turns out that the equation of state is not so bad. It's just the pressure going as the energy density cubed. Okay, P going as rho cubed. For comparison, an ordinary BEC has P going as rho squared. So by the way, BEC has a long history in dark matter community. I'm not the first one to propose it. But the usual dark matter Bose-Einstein condensate that people talk about have this equation of state. Here it's rho cubed. Okay? Knowing the equation of state, under hydrostatic equilibrium, you can compute the density profile of this superfluid. And here it is. It's a chord. Yeah, you just solved the hydrostatic equation. It's a chord density profile. The rho is approximately constant and then drops to 0 at a particular radius. When you plug in numbers to find what is the size, the physical size of the halo, you find something, actually some nice numerical accident, that the radius of the halo, the superfluid core, is actually indeed of order kiloparsecs, tens of kiloparsecs, for mass of the dark matter particle of order eV and the scale lambda of the superfluid of order milli-electron volt. That didn't have to happen, somehow the kiloparsec scale emerges out of this story. I want to stress something important. So, the picture I have in mind is that there would be a superfluid core whose size would be tens of kiloparsec in a galaxy. But outside of that superfluid core, there would be dark matter particles in the normal phase whizzing around. Okay, so you can imagine you have a superfluid core with an envelope outside, which is like NFW profile. That would be the picture. So it's not unlike, for example, fuzzy dark matter, that you have some core, but here, instead of being stabilized by the uncertainty principle, it's stabilized by pressure, classical pressure. Okay, I mean, so here's just some details. The force you get from the phonons is indistinguishable from Mon, but the distinction is that there's not dark matter, and you can show that dark matter inside of this core is pretty negligible inside the core, so you have rotation curves that are governed just by Mon, but of course, by the time you get to the edge of the core, dark matter is important and will influence lensing. Okay. Okay, so now there's a nice story to be said about when does a superfluid description break down. Now,
so Justin,
yes, by all means.
30 kiloparsecs for the size of the core, that sounds really big.
That's right, yeah, so it has to be big enough that the rotation curves, if you want, fit within it. So for a large galaxy like the Milky Way,
is that the core of the rotation curve or the core of the condensate?
Is the core of the condensate.
I see.
But because you have Mon inside, you want to make sure that the rotation curves are governed by Mon. Outside the core, there's no Mon. Yeah. Okay, so now, when does the superfluid description break down? So the velocity, there's a back of the envelope criterion that you can use, which is the following. The velocity of the superfluid is given in terms of the gradient of the phonon. This velocity should always be less, of course, than the critical velocity, the velocity beyond which you no longer have a Bose-Einstein condensate. And you can show that in galaxies, this holds all the way down to kiloparsec distances from the center. Okay, so it's perfectly fine. At distances where you are probing rotation curves, it's fine up to 30 kiloparsec or 50 kiloparsec. When you get down to below kiloparsec size, the story breaks down because the gradients of the phonons get too large. Now, this has an important implication for solar system. In the solar system, on the other, as I said earlier, the Mond component gives a tiny contribution to the acceleration, much smaller than the Newtonian one. But still, it's too large to accommodate constraints from planetary orbits, from deviations from GR in the solar system. So, in the Mond literature, what people have to do is they have to further complicate the theory for a solar system in the solar system scale. Here, on the other hand, you can show that the sun by itself, in the vicinity of the sun would induce such a huge gradient in the phonon that in fact you break down the superfluid. So it's like the sun is like an impurity. The superfluid in the vicinity of the sun breaks down, and so in fact you can work out the size. It's about 1,000 AU. So this is good. It means that in the solar system, the dark matter behaves like ordinary axion-like particles. It's good news for experiments. Yes, go ahead.
So it breaks down. This condensate goes away at large distances.
Yeah.
The way you describe it, short distances, the effective field theory, the effective theory breaks down. You don't know what's happening. Do you know that the condensate is breaking down? Maybe.
Oh, I know what's happening. If I tell you it's breaking down, it's just particles. That's the beauty of it.
But all you're saying is the effective theory no longer describes the system.
That's right, the superfluid effective theory, right? So the idea is that once I say I'm in a superfluid state, describe that when I'm in the superfluid state, the relative degrees of freedom, right? It's like going from quarks to protons, right? When I'm in the superfluid state, the relative degrees of freedom are collective excitations, they're phonon. If the superfluid breaks down, the UV completion of that are just dark matter particles.
It's just where it's breaking down at both extremes. I would thought the overlap in the wave function was in more extreme.
Oh, I see. No, it's different physics, you see. So, so what happens deep in the core, you have large gradients of the phonons. That's the reason for the breakdown. At the edge, it's the density that goes to zero. Okay, so it's a different reason for the breakdown.
So Justin, can I come back to the core size?
Yeah.
I apologize.
No, by all means.
So Mond is good. It behaves Mond-like within 30 kiloparsecs.
Yeah.
Is that what you were saying?
That's what I'm saying.
So, but the asymptotic rotation curve is flat, and that's due to dark matter?
No. It's due to Mond. That's the point.
Okay. Well,
So think about, galaxy rotation curves, depends on the galaxy, but let's say for Milky Way-like galaxy, you probe it out to 30 kiloparsec, maybe 40 kiloparsec for the large ones. The tiny ones like dwarfs, you probe it out to 10 kiloparsecs. So the idea is that where you probe rotation curves and where Mond does a good job, that will lie within the superfluid core. But when you go outside that, these are much larger distances. These are the distances probed by lensing of enough clusters and so on.
so now the dark matter takes.
And now it's the dark matter that takes
But
over.
then how does it solve, like, when you said a chord, I was thinking that you ended up with a density profile that was a chord NFW or something.
Well, that's effectively what it is, but the core, when you're inside the core, the superfluid core, it has approximately constant density. So yeah, your intuition is perfectly fine. So but what happens?
Density from 30 kiloparsecs inward?
Yeah, it's mainly constant. It's subdominant to the Mond force. So there is a dark matter contribution there, but it's totally subdominant. Yeah. So does Andrea have any question?
Yeah, so suppose I find a galaxy with rotation curve out to 100 kiloparsec, where the core is expected to be at 30 kiloparsec.
Yes.
And it's continuous and unbroken. So would it be a problem then, or you have?
It would be a problem. I mean, the dark matter has to take on in such a way that this maintains.
But then you say that
smoothly connects. Yeah.
Right, but then you say that it connects smoothly into NFW, and NFW also predicts roughly flat rotation curve.
Right.
Maybe not. Maybe there is a constraint.
Maybe it's okay.
So
Yeah.
have you computed the total rotation curve?
It's very hard. That's a good question, right? So that's something that I'm thinking about. It's not so easy to do this two-fluid. I mean, in principle, probably two-fluid description can give it to you. I haven't managed to work it out analytically. how to, so far I just have an empirical model, but to actually do a rigorous calculation of the full profile, I haven't managed to do that yet.
Because
Yeah.
just, sorry,
Yeah, by all means.
just to clarify, so
Yeah.
just explaining flat rotation curves out to large radius is not a problem for CDM. It's only detailed shapes within, say, 10 kiloparsecs.
That's right.
There's a variation and more seems to...
Yeah, and if W in principle can give it to you, you're correct. There is one thing, by the way, this comment reminds me, I think with Nick, we were discussing this the other day. There are observations if you stack galaxies, as I understand. Eventually you see Keplerian fall off of the profile. And with that by itself also would be problematic for Mon, because Mon would say it's flat all the way, right? Here, once you're outside the core, it's NFW, so all these observations are perfectly reasonable. Okay, I'm going to move on a little bit. Okay, anyways, this we discussed, perfect, okay. Observational signatures, okay. Now, I have to say, this is all going to be very qualitative, okay? They're mostly hallucinations, not proofs, okay? So once you start thinking about superfluid, you start seeing it all over the place, okay? But, okay, so let's discuss some constraints, some possible qualitative signatures of this picture. Okay, so first the bullet cluster, which we all know. You have two clusters collide, bullet comes in. Of course, the dark matter together with the galaxies, they pass right through unimpeded, but the gas is slowed down by Ramp pressure, and at the end of the day, you have a segregation of gas and lensing peaks. This has been shown to give a bound on the cross-section, on the self-interaction cross-section, velocity-independent cross-section of dark matter to be of order less than 0.5 centimeters squared per gram. Now, I want to say, our cross-section is consistent with this, but more importantly, what superfluid does, superfluid would have the following prediction. Whether you have dissipation of the superfluid or not has to do, at least if you apply the naive Landau criterion, it has to do with the infall velocity of the object compared to the sound speed within the object. That's the Landau's criterion. If you move a superfluid too fast, you go out of superfluid. If it's slow enough, you remain superfluid. That's the criterion. So you can compare the sound speeds within the subcluster, the bullet, and the main cluster, compared to the infall velocity that's estimated by reconstruction, and you find that they're kind of comparable. So one possibility is simply that the bullet comes in, is made of superfluid core, would pass through unimpeded. There's no dynamical friction, there is no friction. Okay, it just passes without dissipation. So indeed, the prediction is that dissipative processes between superfluid cores, at least those that move relative to each other sufficiently slowly, should be suppressed. Now, there is a counter-bullet example, which is ABO 520. Now, this one is more messy, so you cannot do a nice reconstruction of the initial conditions, but it has interesting features. So again, here's the optical image, the X-ray image, which shows a broad lump, but the lensing peak is also spread out, okay? So this is interesting. It's not like the bullet. So if you look at the lensing maps I sort of tilted the image, you see that there are lensing peaks here, lensing peak there, okay, that's totally expected, that's like the bullet. But there's also a big lensing peak which overlaps with the X-ray gas. Now that, qualitatively, to me, may be a signature of the two-fluid model. If the cluster is in a mixture of the two phases, superfluid and normal phase, when there's a collision, you would expect the superfluid phase to pass right through, unimpeded, but the normal phase to lag behind. And that could be a kind of picture that would emerge in these emerging systems. Vortices, it's well known, if you spin a superfluid faster than a critical velocity, it cannot rotate homogeneously. Instead, the angular momentum is carried by an array of vortices. Okay? So here you can show, in fact, that the galaxy itself, the angular momentum of the halo that you expect from simulations is large enough to form an array of vortices. That's what would carry the angular momentum of a dark matter halo in this case. And there's about, I can estimate, there's about one per size of like a solar system. They're pretty light, so do they have any observational consequences? I don't know. Okay, probably not, but it's an interesting fact. Galaxy mergers, I think this is going to be very interesting. So the merger history of halos in our case could be quite different. I expect it to be different than CDM. Because again, so first of all, coming back to Mike's point, so if you have two halos that are separated, there is no superfluid between them, so the force will be ordinary CDM force, ordinary Newtonian force. But when they hit each other, if the infall velocity is less than the virial velocity, or so, 200 kilometers per second, then you expect negligible dynamical friction between the superfluids, and so in general you'd expect a longer merger timescale, fewer mergers, and possibly multiple encounters in the process. If, on the other hand, the infall velocity is large enough, then you'll excite particles out of the condensate, and you will have dynamical friction and merger. So it's an interesting, I think it's an interesting twist on the merger history that will depend on the infall velocity, the relative velocity of halos in time. Oh, incidentally, there is an interesting, curious story with Fornax, one of the dwarf spheroidals around the Milky Way. So Fornax has 5 globular clusters orbiting it. These globular clusters, one would expect, should be within the NFW halo. And with dynamical friction, you would have expected these globular clusters to have merged onto Fornax. The fact that they have not is somewhat puzzling. In CDM, it means that probably there's a core, a pretty big core, and these globular clusters are just outside the core. Here, there's no problem. These globular clusters would just be moving around happily in a superfluid, not experiencing any dissipation, and there's no paradox. There's a story with bars in galaxies that I'm happy to talk about. It's well known that there's a bar instability in CDM, precisely because of dynamical friction. If dynamical friction is suppressed, bars remain small. Okay? So there's some nice features of having less dynamical friction. Experimentally, when you collide 2 lumps of superfluid, this is what people find. This is, again, striking quantum mechanics. If you collide 2 lumps of superfluid below critical velocity, sure, at the end of the day, you get what I said. They come, they merge, they come back. They're unimpeded. They look the same as what they looked like initially. But in the intermediate phase, there's interference. There are fringes because of the coherent phase of the wave function in these lumps. So here, I mean, this is where you hallucinate. But these nice shells that you see around galaxies, they have a perfectly fine explanation within CDM. But this could give an alternative route or an additional mechanism, perhaps, to create these kinds of rings or shells around galaxies. Okay, now there are some distinctions with MON that I want to stress. The key point, as we discussed with Mike, is that if there's no dark matter, then there are no superfluid phonons, there's no MON. Okay, so whenever there's no dark matter, there's no MON. That's important. Remember the story of globular clusters. In the standard picture, they're not expected to have dark matter. Okay, and so there's no MON. That's how you avoid the puzzle of globular clusters with respect to MON. Similarly with the tidal dwarfs, as I said, you strip off the baryons, but you don't strip off the dark matter. They are expected to be dark matter free, and therefore MON free. And so again, that seems to stick. Oh, okay, good. I don't know what time it is actually, but probably I'm speaking too fast. Oh, good, okay. So, now, and this is completely different, for something completely different, okay? What about dark energy? Because that's, of course, the elephant in the room. Yeah, Scott.
Since you have so much extra time, the other elephant, the low mass dark matter structure formation, we're not worried about that? The 2 eV dark matter, that's okay?
2 eV dark matter?
The mass of the thing is 2 eV, that's something terrible too.
No, they never thermalize with ordinary matter. They're like axions. I should have said that. Yeah, this is important. They're really like axions. They're not, yeah, this is good. They're thermal with themselves, but they're basically decoupled from ordinary matter. So they're at millikelvin while the rest of the stuff is high temperature.
And neutrinos don't work as this. They have low enough mass, but they don't have high enough interaction.
Exactly. It's a cross-section that's not too low.
So they can't.
Right, this cross-section, just like self-interacting dark matter, is like a strong type. Huh? And they're fermions.
Could you just talk about the cosmology of it? So do they condense into the universe like axions?
They do. So rapidly after they're formed. So they're formed like axions, let's say with some vacuum misalignment. They condense to form superfluid. So for most of the history, they're superfluid on large scales, which is fine. After all, dark matter is a superfluid on large scales. So it's totally fine. What happens when you start forming structure, however, is that now if you form a large enough halo, then you'll start, these particles start acquiring velocity and they start heating up. They'll rethermalize at a higher temperature. And now what? Yeah.
So there's only nonlinear structures. So the
exactly.
background is just the same as usual.
Oh yeah. There's no, exactly. So all the large scale observables are the same because after all we treat dark matter as a superfluid in the textbooks. Yeah.
So this picture, is it true that you don't have WIMPs anymore?
Yeah, there's no WIMPs. This is just like axions.
Okay, so
With
That's what you're wrong.
sorry.
So you can't look for axions. So
You can, yeah. I had a picture of ADMX on the slide, yeah.
Except that that's a QCD axon.
It doesn't matter. So these operators, QCD of course has this whole story, but QCD axons, I mean, but here, it's an axon-like particle that has approximate shift symmetry. You can couple it in the way you couple axions.
But you don't have to couple it, so you don't look for it. Yeah.
You don't have to couple it, yes, exactly. But you might, okay, so. You don't have to, but it's something you can constrain.
You have an X mandate.
Could be a true.
Yeah. Let me move on to dark energy. Okay, so I want to talk about, this is totally different, okay? This is for Wade to some extent. Totally different. So I've never talked about this topic, okay? But I think this is kind of fun, okay? It is related to superfluid, in that you'll see it uses the same building blocks. But I think it's a new type of idea. Okay, so here's a sort of broad story about the different approaches to cosmic acceleration. There are two paths, really. For cosmic acceleration, either you postulate dark energy or some form of negative pressure, which couples to ordinary gravity, or you postulate, people study so-called modified gravity. To me, that just means new degrees of freedom, which you can think about as being part of gravity, doesn't matter. So it's one or the other, right? Either it's dark negative pressure, or you must introduce new degrees of freedom, because of course GR by itself, without ceasing. That's that. Yeah. And anything with negative pressure, I call dark energy. So I want to show that in fact there's a third possibility, okay? I think, which is cosmic acceleration without negative pressure and without new degrees of freedom. Meaning I'm only doing it with dark matter and baryons. That's it. And they interact with each other. Okay, so there's no dark energy, no new degrees of freedom. I think it holds water, at least at the first pass, but let's see if it holds this long. Okay, so here's the idea. This is work in progress with Lasha and another postdoc, Jung Huang. So imagine, this is just ordinary gravity with only dark matter in Einstein frame. Okay, so clearly, the expansion history is Einstein de Sitter, all the way to today. There's no accelerated expansion in this Einstein frame. But baryons, ordinary matter, couple to, not to this metric, it couples to a so-called Jordan frame metric, a different metric. Let's call it G tilde, which is a function of the dark matter. This is the same X as what we discussed earlier. It's a proxy for the dark matter density. It's a function of the dark matter density times this Einstein frame metric. In other words, baryons feel a scale factor, which is a function of X times the Einstein frame scale factor. So although this scale factor is decelerating, okay, it's Einstein de Sitter, because if omega of X grows in time, the observed scale factor can be accelerated and produce cosmic acceleration. It only arises because dark matter couples to ordinary matter, not because of
Baryons means photons also.
It means photons also. Very good. Absolutely. Yeah. Everything couples to this metric. We can come back to photons a little bit later. So indeed, this omega of X, just schematically, what kind of form can it have? At high density, high X, this is high dark matter density, one imposes phenomenologically that it tends to 1. Okay, so that at high density, you recover ordinary story, ordinary gravity, no coupling between dark matter and baryons. But then at low enough density, namely compared to the density today, this omega function grows and triggers cosmic acceleration. Of course, you have to put in that scale by hand. I'm not doing anything. I'm not performing miracles. Okay, now, but it's interesting. This is like a screening mechanism because it tells you that at high density, namely in the early universe or deep inside halo, you have ordinary story. There's no modification, okay, just ordinary story. Only at densities comparable to the mean density today, you see a difference. So in particular, clearly I can choose this function to reproduce any cosmic history I want. I can reproduce lambda CDM exactly if I want. Here's just an example. We picked one function out of a hat which satisfies these asymptotic conditions. And you see you can reproduce the luminosity distance almost degenerately with lambda CDM. Now there's an interesting twist because it's not lambda CDM. So for example, now you start asking about cosmological parameters. You know that there's a well-known 2 sigma tension in the Hubble parameter between the CMB inferred value, inferred by assuming lambda CDM, it's an indirect measurement, to direct measurements of the Hubble parameter from supernova and so forth. Okay, we find a different value which happily sits in between, but it reduces the tension if there is a tension. Now, what about growth? Okay, because we know it's not just the expansion history. We know about dark energy because it slows down the growth of structure at late times. So what about that? So now, naively, this looks like trouble from the beginning, because after all, in this story, we just have Einstein de Sitter expansion. Dark matter just feels Einstein de Sitter, so therefore density perturbations will grow as a scale factor, just like the textbook CDM, no lambda. So doesn't that mean we're going to have too much growth? But if you think about it, baryons don't observe this scale factor. You should ask the question about the scale, relative to the scale factor that they measure. So the actual rate of growth is really to be measured relative to the physical scale factor, and it's down by exactly this power of omega. So you slow down growth by the same factor that you produce acceleration. In fact, if you want, I don't know, I tell this intuition to people, some people think it doesn't help them, it confuses them more. It helps me, so I tell you. The intuition is that if you want, the Einstein frame universe, this universe in which it just expands as Einstein de Sitter, is actually a younger universe than it would appear. It's a younger universe than the measured universe for the baryons. So it's a CDM universe, but let's say it's like 10 billion year old universe, compared to the 14 billion years that baryons experience. So if you want, this is the structures that are seen by the baryons for a 14 billion year old universe. This is the structures that a pure CDM universe of the same age would look like. So baryons conclude structures are undeveloped, therefore there must be dark energy as well. You can compute the growth function, okay, it's different, and indeed, you find happily, again, there's some mild tension on sigma 8, you find sigma 8 value which is closer to the Planck value, than, anyways, it's sort of, which is closer to the weak lensing value, than the lambda CDM, higher value that's found with the CMB. The growth rate is also interesting. If you compute this growth rate times sigma 8, there's some well-known, again, mild tensions at a high redshift, so that the dashed line is a lambda CDM value, okay, with a band here. These are various surveys, and the solid line is our model, and it predicts, indeed, at high redshift, you go under. Okay, so there's less F sigma 8 is below lambda CDM. Anyways, this is for fun. It's the last 2 minutes, but this is what I'm thinking about at the moment. Yeah, Andre.
So what omega matter is 1 here? Or?
Good. So it's not 1. It's 1 from the point of view of the Einstein frame. From the Jordan frame observers, they feel like Newton's constant is evolving in time. So there are additional contributions in the Friedmann equation. So its omega matter is 0.3 from the point of view of baryons.
So if I measure it in clusters, if I measure dynamically mass and for total mass and baryons, I would still get normal baryons?
Absolutely, because you divide by the total energy density of the universe, and that total energy density of the universe is larger. So still omega matter is 0.3.
What does the scale factor do asymptotically?
Oh, that's model dependent, but it can do all kinds of.
But it's not exponent. It's
No, it could. So, I mean, what I would suspect physically is that this growth asymptotes also to a constant. So eventually, you would revert back to a CDM, pure CDM universe.
And why now?
Huh?
So how do you address the why now? Why
I don't address it. I don't address it. So, I'm not, look, okay, this is interesting. It's not, I'm not presenting this as a better model. I just want to say, as a proof of principle, there's a third alternative. There's no negative pressure here, there's no new degrees of freedom, and yet I'm producing cosmic acceleration. So it's like a third avenue. It's like a loophole in some theorems that nobody spelled out. Okay, anyways, to conclude, so I think everybody agrees that the small scale stuff, galaxy scales, is indeed where the greatest challenge lies for lambda CDM. So I presented an idea. I don't know, it's maybe not likely to be true, but on the other hand, Trump being president is also an unlikely event. If there's a multiverse and we happen to be in the branch where Donald Trump happens, maybe this stuff happens. And so the idea is that the dark matter and MON really are unified. They're different manifestations of the same underlying substance. All the scales from the particle physics point of view, they're comparable, which is something that I like. They're all EV or so-ish. Phenomenologically, there are a lot of predictions that distinguish it from CDM, but also from MON. So if there's no dark matter, there's no MON, and that's helpful for a bunch of systems. There's a bunch of open questions. The most interesting one would be, can I find an actual cold atom system that has this equation of state? I said the unitary Fermi gas looks like that, but can I find an actual precise cold atom system? That would be very cool. In a laboratory, you can imagine simulating galaxy dynamics with cold atoms. Okay, that's the fantasy. There are other ways, there are other ways to realize MON here, not just the one I showed you. All I'm doing is using the fact that if you have superfluidity, it gives you a classical scalar field. a coherent scalar field, which is the phase of the wave function. So there are all kinds of ways you can get things like MON or modified gravity. And finally, dark energy, I think, is kind of interesting to see how it might fit as yet another part of the puzzle. Thank you. No, it's derived, and it's derived from lambda. So, I mean, I chose lambda to get A0 out. But so the way it comes out is the same numerology that you normally get. A0 is like geometric, whatever it comes out to be.
Which is the fundamental parameter of Lagrange? Is it A0 or is it A?
It's lambda. That's the scale of the superfluid. And it's the usual thing that if you take the geometric mean of the Hubble parameter and then plot, you get the
Yeah,
mean.
those models somehow don't exploit that.
Yeah, I do. I don't know. Can't speak for everybody.
I think what's satisfactory about MON, right, is that they take one small subset of observations, rotation curves, right, and you can come up with a comparable better description. But it's still about any observation, and any observation can these thousands of theories that fit this particular one. Problem that we have to fit everything, right? We cannot allow us to pick observations. So
I agree.
Change the force of this large size. The full dynamics of disk become different, right? The atomic instability criteria, bar formation, pouch formation, everything that becomes completely different. Right?
That's right.
So then you have to actually demonstrate that you're not getting something crazy like pouches the size of the disk or disk.
I agree. There's a lot of things to be checked. Okay, there's a lot of things to be checked. I think it would be interesting to check that. It's a proposal, but I agree. It's motivated by MON. It improves on certain things about MON, but I better make sure that I get realistic galaxies at the end of the day.
I mean, can you kill the dinosaurs?
Can't you feel one?
Like the next. So you mentioned that stars were impurities, right?
Yes.
Do you have too many impurities close to each other?
No, it's very, I mean, no, look, the size was 1,000 AU, but the size of the atmosphere.
So, in some sense, these are like axions that you're relying on some sort of misalignment reduction, presumably?
Yeah.
Or something like that?
Yeah.
But unlike axions, they've also got very strong self-interaction.
Indeed, they do.
And so I'm just wondering whether that should change how we think about the production mechanism, or whether that spoils what we would naively expect from this alignment.
It's a good question. I haven't thought in detail about the production mechanism. We work something to think about.
How do you search for the axion-like particles?
Oh, there are various ways. So one way is if they couple to FF tilde, right? You can have, if you couple to the electromagnetic, F mu tilde, then you can have an axion photon oscillation. People look at this like with light shining through the walls. So there are various methods that people exploit.
Is this right for EV scale? I know ADMX is more tuned to the micro EV scale.
Indeed. So indeed, axions, you can look for them. I mean, now I think you go up to 10 to the minus 5 EV. People are trying to push to 10 to the minus 4. I mean, the higher the mass, the harder it is because you have to get cavities of even smaller size. So EV probably is hopeless, but okay. Anyways, it's interesting. It's very interesting. Greg.
A little bit more about the vortex moments.
Yeah.
So there are defects where that know all the angular moments.
Correct.
Are they density in homogeneities?
They are density homogeneities.
So
Yeah.
they're like strings. So they're turning the galaxy
They're exactly like springs.
and moving around either the speed of light or the galactic velocity.
No, the way I think about it, they're just standing still, right? It's like
So
yeah.
they're moving in typical.
They're moving some typical velocity.
So how could you see them?
Yeah, that's right. So when I estimated their density, their mass, if you want, they're quite light. So the idea might be through gravitational lensing, you could see a signature. I think they're too light to be seen in gravitational lensing. But yeah, it's very interesting. But right now, I don't think they can be easily observed.
So superfluid, you can trap light particles on a vortex. You'll trap light stars on a vortex.
Wow, that's interesting. Yeah.
Just look through
Yeah.
a string of
Interesting.
Yeah. Oops.
So the self-interactions that have to be very strong.
Yeah.
Okay, so those are
Strong.
the things that thermalize them.
That's right.
But the interactions to photons or other particles don't have to be strong.
No, they're quite weak. They're M-plus first.
Okay, so things that destroy them or create them can be very weak interactions. So that probably doesn't affect their abundance.
No, that's right. That's why they are.
Because
That's right.
they just scatter very effectively.
Exactly. With one another, but not with the rest of them.
Have to be.
Sorry, there's one person that's been waiting for a long time. Okay. Yes, please.
So I have two questions. So the first is, if I were to have a superfluid core, and I had a stream of dark matter particles fall towards it, do they stick or do they pass through?
Good. It depends on the velocity of those particles relative to the superfluid. If they're above critical velocity, along their way, they will start to excite particles out of the condensate and be slowed down by angular friction. And they're slow enough to pass through on.
Okay. And then my second question is that when we simulate cold dark matter halos and we include baryonic physics in it, we know that perturbs the potential significantly.
Yes.
And yet the match that you get is to a completely unperturbed potential. So is there a reason that we would expect that we wouldn't see a similarly large deviation?
Good. Right. So that's a good question. That's an excellent question. So when I mentioned at the beginning these departures from here, these departures at low mass from the Baryons-Kelly-Fisher relationship, in my model this would be the product of feedback. So at sufficiently low mass, yes, feedback occurs, you disturb the baryons, and there you go, you start seeing deviations. It's just the difference is that maybe a difference between the standard discussion is that feedback doesn't affect these galaxies as much. They would only weaken at lower mass. These are detailed questions, whether...
Do you know that feedback has to operate on the bulk of the baryons at very large stages? Because that's where all the baryons are. You don't have them. You know how many baryons there are not.
You mean because the missing baryon?
Yeah,
Right.
Yeah, so a lot more
Right.
baryons.
That's right. That's right. Yeah, so that picture is the same.
Feedback still.
How big does the perturber need to be to cause dynamical friction? Like, we have hypervelocity stars presumably coming out from the center of the galaxy. Should they slow down before they get to the halo?
Sorry, can you say?
You know about hypervelocity stars?
No.
Okay, they're coming out at like 500 kilometers per second from the center of the galaxy. And so that's higher than typical dwarf galaxies are coming through the halo.
Good. So if they have that kind of velocity, they would be slowed down by dynamical friction, but in the same way that they would be in CDM. I'm not saying they would be slowed down more.
Okay, so
it would just be, the story would revert to CDM.